Okay, let me start. Okay, last class, what we were looking at is R is a ring and alpha. We are attaching and adjoining a new element alpha to R, where alpha satisfies some relation over Q over R. Okay, so the same thing we can able to do it for finitely many more several elements. Alpha 1, alpha 2, alpha n can be adjoined by repeating the same procedure or by introducing appropriate relation in the polynomial ring R of x1, x2, xn in n variable all at once. Okay, this all at once means you do it together or one by one, that both rings are going to be isomorphic. That and all we have seen already. Okay, the important case in this adjoining is the relation satisfied by that alpha is a kind of polynomial relation and it is monic polynomial relation. That is an important case for us of study. The new element alpha is required to satisfy a single monic equation of degree n, which is positive. Suppose we want the relation f of x equal to 0, where f is monic of this kind, where Ca is of the coefficient coming from R, the ring, then the following proposition precisely describing the ring R of alpha. R of alpha is the new ring adjoining alpha to R. Okay. So how it is structure is R is a ring. F of x is a monic polynomial of positive degree n with coefficient in R. Let R of alpha denote the ring obtained by adjoining an element satisfying the relation f of alpha equal to 0. Okay, the elements of R of alpha, you take any element, then you can send a kind of, you send it to R1, R0, R1, R2, etc., Rn minus 1, which is a n tuple in the ring R power n. Okay. So similarly, given any element in R power n, I can get one element of the ring R of alpha. Okay. So it means the elements are in bijective correspondence with the vectors n tuple in Rn. This is what we want to prove. This is already we have seen in many kind of situation. Since R of alpha is the quotient of the polynomial ring Rx, okay, every element in R of alpha, how it look like? It is a residue of a polynomial, okay, in alpha. This means that this can be written in the form of G of alpha for some polynomial gx inside Rx. The relation f of alpha equal to 0 can be used to replace any polynomial g of alpha of degree greater than or equal to n by one of the lower degree. Okay, what we meant is we perform the division with a remainder by f of x. This is possible because f of x is monic polynomial we have chosen from Rx. Therefore, the division algorithm is true. Okay, so given any polynomial g of x and f of x is monic polynomial, we can divide and look at the remainder R of x, whose R of x's degree is strictly less than the degree of f of x. Okay, either it is 0, completely 0 polynomial, or degree is strictly less. So when you plug alpha into x, g of alpha, which is since f of alpha is 0, then this will become R of alpha in the R of alpha ring. Okay, thus every element beta can be written as a polynomial in alpha of degree strictly less than n. Okay, then and each polynomial g of alpha, g of alpha in alpha of degree strictly less than n can be mapped to R0, R1, Rn minus 1, where R0, R1, Rn minus 1 are the coefficient of g of x. Okay. Now we show that the principal ideal generated by f of x. Okay, so what we have shown is just we have given a map how element of R of alpha goes to as a n tuple. and n tuple is given, then you can find one element in R of alpha. Why? Because n tuple is given, then you just form, suppose R0, R1, Rn minus 1 is given, then we form a polynomial R0 plus R1x, etc., Rn minus 1 x power n minus 1. That is in R0 plus R1 alpha, etc., Rn minus 1 alpha power n minus 1, then it is inside R of alpha. Okay, so that's all. We have given a map. We want to say that it is bijective correspondence in some sense. The ontoness is coming from here, injective we want. Okay. Okay, so what it says, okay. So this is the last line. Now we show that the principal ideal generated by f of x. Okay, that f of x, why we are looking at the principal ideal? Because R of alpha will look like is isomorphic to Rx modulo the principal ideal generated by f of x. Okay, that is the way R of alpha is defined. Okay, the principal ideal cannot contain any element of degree strictly less than n. Okay, it so that we have to kind of show, and therefore g of alpha is non-zero always in the whatever any g in any g of degree strictly less than n, and you plug alpha, then g of alpha is non-zero. Okay, for every non-zero polynomial gx of degree n. So this will imply that the expression in terms of degree strictly less than n for any beta is unique. Why it is unique? Suppose if two representation is there, g1 of alpha and g2 alpha both are representing beta, then g1 of alpha equal to g2 of alpha. That means g1 of alpha minus g2 of alpha is 0. But the point is g1 and g2 are two different polynomial, okay, and of degree strictly less than n. Therefore, the polynomial g1 minus g2 is of degree strictly less than n, and alpha is 0. Okay, so that will contradict. If we prove that g of alpha anything less than degree n will not be inside the ideal generated by f of x, that implies that this beta is unique. The expression is unique. It means it is bijective correspondence. Okay, that is the reason. So you just look at the principal ideal generated by f of x. Okay, that means set of all multiples h of x times f of x of f of x. That's the principal ideal. So if h of x is like bm x power m plus etc. plus b naught, where bm is the leading coefficient which is non-zero. Okay, then the highest degree term of the product h of x and f of x is bm times x power m plus n, because f of x highest leading term is 1 because it is monic. Okay, so the highest leading term in the product is bm only, since it is non-zero and m plus n is greater than or equal to n. So the degree is always, for the product, degree is always greater than or equal to n. Nothing will less than n will be inside the ideal, okay, generated by f of x. Okay, so this says that so suppose if we adjoin alpha a element to the ring R, where alpha satisfies a relation with monic relation in polynomial relation, but monic, then R of alpha is like R of alpha has a basis. Okay, R of alpha has kind of basis 1 alpha square up to alpha power n, where alpha power n minus 1. This proposition says that the powers 1 alpha power n minus 1 forms a basis of R of alpha over R. Kind of every element of R of alpha can be uniquely expressed as a linear combination of this. That's what the above proposition proves. Okay, of course, to multiply two such a linear combination in R of alpha, we can use the polynomial multiplication and then divide by f of x. The remainder is the linear combination of this particular thing. Already it has been, just I'm once more telling. Okay, we will see example. So, okay, alpha is an element satisfying the polynomial relation with monic. Alpha cube plus 3, alpha plus 1 equal to 0. Okay, 3, the coefficients are integers. So we are going to look at the ring, extension ring of Z of alpha, that is R prime. The R prime, how we would have got it? We just look at the polynomial ring ZX modulo the ideal generated by x cube plus 3x plus 1. Okay, so since we are quotienting it, what are the we are quotienting a polynomial generated by 3 degree. So every element of the R prime is a linear combination of 1 alpha alpha square by the previous proposition. Okay, that is nothing but R0 plus R1 alpha plus R2 alpha square. Okay, addition. So for instance, 2 elements I have taken, 2 plus alpha minus alpha square, 1 plus alpha. The addition is just usual addition. The likewise power you just add. Multiplication, when we multiply completely, then we will get alpha cube. Alpha cube has to be replaced by the lower one. For that, how we do? We do it 2 different way. Alpha cube equal to minus 3 alpha minus 1. So therefore, wherever alpha cube comes, you replace it by minus 3 alpha minus 1 in that multiplication. Okay, so then it reduces to just 1 alpha alpha square relation. In other way, I mean, just you divide by 1 plus 3 alpha plus alpha cube. The multiplication you have multiplied. When you multiply these 2 elements, you get this element. This element is divided by that relation 1 plus 3 alpha plus alpha cube. Then you get the remainder. That is the one. This element is same as the remainder. Okay. Okay. So another example. So R prime is a ring obtained by alpha to the finite field of 5 elements. Okay, F5 is a finite field of 5 elements where alpha satisfies alpha square minus 3 equal to 0. So this means that R prime is nothing but, we look at the polynomial ring F5 of x modulo the ideal generated by x square minus 3. Okay, so clearly alpha represents a formal square root of 3 in R prime. Okay, why? Because alpha satisfies, it means alpha square equal to 3. Alpha is an element in that ring R prime. It's not inside F5, but it is inside R prime. Okay, so therefore the square root of 3 is represented by alpha, formal square root. Okay, any element in this ring, since degree of that principal idea, the degree of the polynomial relation satisfied by alpha is 2. Therefore, every element in R prime looks like 1 plus B alpha only. Okay, so here you see what we got is adjoining ring. Here R prime is going to be a field. Why it is a field? So indeed, to prove if it is a field, okay, to prove it is a field, what we have to prove, every non-zero element has an inverse, because the ring structure is already there, commutativity is there. Then just we have to prove the inverse. Every non-zero element inverse exists. So we start with a non-zero element A plus B alpha, which is non-zero in R prime, and you look at this 2 element product A plus B alpha times A minus B alpha. This is same as A square minus B square alpha square. Alpha square satisfies alpha square is nothing but 3. Therefore, this is same as A square minus 3B square, where A and B are coming from what? Where A and B are coming from? It's in the F5. Okay, in the finite field F5. Okay, so A square minus 3B square is a non-zero element in F5. Why? How it is known? Anybody knows? A and B are coming from F5. Okay, so A square minus 3B square is non-zero. I'm saying, I am asserting that a square minus 3b square is non-zero in Fi, finite field Fi.
Because 3 is
How
not a quadratic residue modulo 5.
Okay. If it is, suppose, if it is, then what happens? If it is, then you see, if it is 0, then a by b whole square equal to 3. Okay, 3 if it is 0, if it is, this relation is 0 means a square, a by b square. See, both has to be non-zero first of all. If one of them is 0, then other one has to be 0. 0, 0 is not a solution of this. 0, 0 is a solution of this. Okay, we are assuming that 0, 0 is a solution. Okay, we have to. Yeah, a and b cannot be 0, 0 just because we have taken a plus b alpha, which is not 0. Therefore, a and b simultaneously cannot be 0. Okay, so that is a contradiction. So that means a by b whole square equal to 3. 3 is a square in Fi. Okay, 3 is a square in Fi. So this you can able to check whether 3 is a square in Fi or not. You just you look at how many elements are there. 5 elements are there. 0 square, 0 is not equal to 3. 1 square, 1 is not equal to 3. 2 square, 2 square is 4. 4 is nothing. 4 is not equal to 3. Then 3 square, 3 square is 9. That is again 4 modulo 5. Then 5 square is anyway 0. So therefore it is 3 is not a perfect square. Therefore it is non-zero. Okay, that is the way. So quadratic residue, if one knows, then one can do. Otherwise you can just simply check. Okay, so therefore once it is non-zero in the field, finite field Fi, then it is it has got inverse. So we just multiply by its inverse. Then we see that a plus b alpha is a inverse. It inverse exists. Okay, so in R prime. So therefore R prime becomes a field. So the previous example is it is not a field, it is a ring. But in this example, it is it becomes a field. Okay. Instead of F5, okay, instead of F5, if we consider F11, the same polynomial we take F11, then you see x square minus 3, we can break into 2, x minus 5 into x plus 5. Okay, so then this is nonsense. Okay, so this you cannot get field, the image. If you change the kind of base I mean ring different, then you cannot expect the similar thing. Okay, the polynomial is same, but the point is field is different. Okay. So far main important case, as we said, we looked at the adjoining of a ring. Okay, element adjoining of a ring. Okay, that element is satisfying a relation with the monic polynomial. Suppose the why we are looking at monic is, first of all, we are using that division algorithm. That maybe that is because of that, I don't know. But we will try to see, suppose if it is the relation is non-monic somewhere, then it is hard to analyze. Okay, hard to analyze the ring structure. A element satisfying a relation, okay, with non-monic kind of polynomial, then and we are adjoining to a ring R, that element, and then this structure is not as nice as the previous one. Okay, so we see with the example, one important case is adjoining a multiplicative inverse. Suppose since R is a ring, not all non-zero element has a multiplicative inverse, right? So suppose some element A which doesn't have a inverse, so we just adjoin the inverse to this ring. Then that extension ring will have the where A will have inverse. Okay, so with that idea, we just start this. So if A belongs to R has an inverse alpha, alpha may not exist inside R. Okay, then the new element we are going to attach to. So it means what relation it satisfies? It satisfies A alpha minus 1 equal to 0. Okay, if alpha is an inverse in somewhere, okay, A alpha minus 1 equal to 0, it will satisfy. Okay, so we adjoin an inverse by forming the quotient ring. Okay, A is inside R. Therefore, what we are looking at the polynomial ax minus 1, and we are looking at the ideal generated by ax minus 1, and we are quotienting that ideal, okay, with rx. That is our r prime. The residue of x becomes the inverse of alpha. Correct? This R has no basis of the type described in the previous proposition, but we can compute what does this look like. Okay, the claim is that this every element, any element in R prime has the, it is of the form alpha power k times R. Alpha is inside R prime. Okay, so every element will look like alpha power k times R. R is coming from the base ring. Okay, for some integer, for non-negative integer k. Okay, so how we are proving? So any element, first of all, any element will look like, it is like R of alpha, right? R prime is like R of alpha because of this quotient. So beta, any element beta inside this R prime will look like a polynomial in R alpha. Okay, some degree. So I call it a kind of n minus 1. So in this polynomial, we are going to put the relation a alpha equal to 1. Okay, a alpha equal to 1. Okay, so it means what I am doing, I am dividing, I am multiplying by a power n minus 1, dividing by a power n minus 1 with beta. Okay, when we do that, you see r naught plus r naught times a power n minus 1 plus etc. plus r n minus 1 times alpha power n minus 1, a power n minus 1 will be there. That will be 1. And then okay, 1 by a power n minus 1 will be there. 1 by a power n minus 1 is same as alpha power n minus 1. This is what you will get. So what you do, take any element R prime that is looks like a polynomial relation in alpha of some degree. So I am just multiplying that beta by a power n minus 1 divided by a power n minus 1. Therefore, I will get beta only. That when I do this, this will become like this: alpha power n minus 1 times some element of the base ring. A belongs to base ring, R belongs to etc. This one you will see that everything inside base ring. If you just multiply correctly, you will see that there is no alpha will be inside. Everything will be killed. So that's why I have taken out in some sense. Okay. So Ri belongs to capital R, and so A belongs to R. The whole thing will be inside R. Therefore, beta can be written as R times alpha power n minus 1 for some R in the ring, base ring. So this is a ring, and every element will look like kind of alpha power, whatever we are attaching, alpha power k times some element of the ring. Okay. Okay. So another example. So we look at a polynomial ring. Polynomial ring over, that is our R is nothing but a polynomial ring over a field F. That is, we write it like a f of t. F of t is a set of is a polynomial ring over F with in variable t. Now we want to adjoin the inverse of the variable t. It means t inverse we want to adjoin. Okay. So it means what we are doing, we are looking at R of x, the polynomial ring R of x, and going by quotient xt minus 1. Inverse means it satisfies xt minus 1, the polynomial. So look at the ideal generated by xt minus 1, you quotient it. R of x quotienting by xt minus 1. R of x is nothing but R of f of t comma x. This already we have seen. We are attaching one variable to the another one variable polynomial, attach another variable. This is isomorphic to attaching as if two variables. Okay. So this R prime will look like R of t inverse, which is same as f of t comma t inverse. This is called a ring of Lorentz polynomial in T. What is Lorentz polynomial? Lorentz polynomial is a polynomial in T and T inverse. This is like this. Negative powers as well as positive powers will be there. Minus n to n, it is not necessary that it is symmetric. Some coefficient can be 0. Okay. So I have written like a symmetric way. Okay. Minus n to n, ai t power I, where a is coming from the field F. Okay. So any element here will look like this one only. That you can just check. Just you take beta belongs to R prime. R prime means R of T inverse. Any element will look like a polynomial in T prime. T inverse. Polynomial in T inverse. Okay. So then, but coefficients are coming from R. R is nothing but F of T. Therefore, AIs are going to be a polynomial in T. So when you plug it completely, you will get of this kind, F of T, Lorentz polynomial. Okay. Okay. So far what we have seen is R is a given ring. We wanted to extend by adjoining. Okay. So how we did that extension business? We are looking at the polynomial ring Rx, and that new element satisfying some relation. We look at the polynomial relation and generated the polynomial relation generated. We generate the ideal, principal ideal generated by the polynomial relation and go modulo that. That is R of alpha. Okay. So here we have not proven yet that R is really sitting inside R of alpha. Okay. So far we have not proved. Okay. When we adjoin an element alpha to a ring R and impose some relation, will the original R will be a subring of R of alpha. Original R is a subring of the ring R of alpha. Okay. So we know R is sitting inside R of X as a subring, okay, of constant polynomials. So the restriction of the canonical map pi from Rx to R modulo I, where I is the kind of relation ideal generated by the relation satisfied by alpha. Okay. So in the canonical map, you look at the canonical map Rx to the quotient ring Rx modulo I, which is nothing but R of alpha. And restrict this is defined for whole ring, and we are restricting to the subring of constant polynomials. That restriction is nothing but we call it psi. Psi is from the ring R to R of alpha. Okay. So this is nothing but the restriction map of the canonical map. How it goes? Canonical map, any polynomial goes to polynomial plus I. Okay. The polynomial bar. Okay. Here only constant polynomial element of R. So R goes to R plus I, R bar. Okay. So for where R belongs to R. The kernel of this psi map is what? Kernel is nothing but R belongs to R, set of R such that R bar is 0. Okay. This is a restriction map of pi. What is the kernel in pi? Pi map? Anybody can tell? Pi is a canonical map. F of x goes to f of x plus I, the coset. Okay. I is the kernel. I am restricting pi, okay, to the subring. Therefore, whatever is R intersection I, that is the kernel of psi, right? That is clear. This is a restriction map, nothing more. Whatever R subring, you are restricting that kernel also in R, okay, to the subring. So R intersection I, R contains, okay, R contains what? R intersection I, how many elements can contain? What are the elements can contain? So what we want to say is that, okay, we want to say R is sitting inside, right? R is sitting inside, we want to say. Okay. So it means kernel psi should be 0. That's all we want to say. Kernel psi should be 0. Okay. That's what we want to say. Yes. Okay.
Yes, sir. Yes.
Yeah.
Then it will be
So whether it is really it is 0. Really it is 0. The constant is 0. This is here it is R belongs to R such that this is inside. Okay. So what happens? R bar is 0 means what? R plus I equal to I. That means R belongs to I. Right? R belongs to I. R belongs to I means what? R is a kind of coefficient which belongs to I. Okay. I is what? Generated by a polynomial. So therefore, the some element R is equal to some product of polynomials. Okay. R is equal to product of polynomials. That's what it says, right? No. Whether you see, I have just written it is a psi is an injective map. Whether it is clear or not, that's what I'm worrying. Okay. It's a product of polynomials. You see, kernel psi has to be 0. Why? Because if R belongs to the coefficient belongs to the ideal, where ideal is generated by f of x of degree n bigger than or equal to 1. Okay, then the coefficient one R element, the coefficient ring element is a product of what? This two polynomials, f of x and g of x. F of x times g of x for some g of x. Whether it is possible.
no.
But why?
We are saying that constant is equals to product of some polynomial.
Yes.
How is it possible?
No. How it is possible? I don't know.
Sir, sir, I contains equations like in terms of coefficients with R and in X, but R all are like constants. Then the intersection
No,
must be
you see, the R
0.
is like f of x times g of x, right? So f is what? F is the generating polynomial, where that alpha is 0, right? I want to understand what is this R. This is the way you check your integral as the abstract integral plus a constant. How do you check? Some special value you check, right? So f of alpha, g of alpha. So f of alpha is 0, therefore R has to be 0 only. There is no other go. This is the way. Is it correct? So I know that f of x. So if I plug alpha in f of x is 0. F of alpha is 0, right? So I have a kind of equation R equal to f of x times g of x. I plug x equal to alpha, then R equal to 0 only I will get. Okay, whatever here I will get this way only. Because you see, if it is a field, I can argue, oh, okay, some unit element will be there, therefore it will become a whole ring kind of. Okay, so that is R is a ring. So we don't know whether unit element is inside or not in this intersection. Okay, so this is the way to argue. But somehow I have written some different argument. R is corresponding to this way. Okay, this way in Rn, which is bijective. Okay, I don't know what I have written, but this is the way to give an argument, one argument. So psi is an injective map. So we are just looking at the canonical map Rx to the quotient ring, which is nothing but R of alpha. Okay, the I is generated by the relation polynomial relation defined by relation by alpha, satisfied by alpha. And then we restrict this pi to the subring of constant polynomials. That restriction map, we call it psi. This psi is injective in this case. In this case, it is injective. Okay, in this case, it is injective. In general, it is not going to be injective. See, here it is monic is really important. Monic is really important. Okay, in this case, it is somehow I have given. Maybe I will think about it whether I have given correct argument or not. Here, monic is really important. We need to use this proposition. Okay, so why? Because if the alpha is not satisfied by monic, non-monic, suppose satisfies non-monic polynomial relation, then we have a counterexample. So this is the counterexample. What is that counterexample? Suppose I have a ring R and I have two elements. I have two elements A and B such that A times B is 0. Okay. So if A is, then A cannot be invertible unless B is 0. Okay. Why? Suppose A is invertible, then I multiply by A inverse, invertible in R. A is invertible in R. That's the assumption I'm making. Then I multiply by A inverse both side of the equation. Then I will force to get B equal to 0. Okay. So therefore, so if B is non-zero, then we can say that A is not invertible in R. So assume that B is non-zero. Once we make an assumption B is non-zero, A is not invertible in R. So we try to adjoin A inverse to R. It means what we are doing, we are looking at the ideal generated by A times x minus 1 in Rx. Then, okay, this ideal Ax minus 1, ideal generated by Ax minus 1, unfortunately captures B also. Why? It contains B. B can be written as minus B times Ax minus 1, because you see B times A or A times B is 0. Here it is commutative. Okay, it is 0. Therefore, it is nothing but B. B can be written as B times Ax minus 1. Okay, which shows that the residue of B in this case is 0. Okay, A times B is already 0. Therefore, A bar, B bar is 0. Okay, so this is kind of going to create a problem. This is going to create a problem. We will see why it is creating a problem. This once AB is 0, then B has to be 0 in the residue field. Whatever, once we adjoin A inverse. Why this is? We are seeing only counterexample, so we give an example. Okay, so in Z mod 6Z, we have two elements, non-zero elements. 2 times 3 is 0. Okay, we try to adjoin 3 inverse to Z mod 6Z. Okay, so by the same procedure, the 2 will become 0 here. Okay, 2 will become 0 here by the same procedure. It's you see in the residue field, residue ring, the 2 will become 0 in R prime. R prime is what? The ring R is Z mod 6 of X, okay, Rx, and we are going modulo the ideal generated by 3 bar X minus 1 bar. Okay, so this R prime is isomorphic to F2. We claim that. So if we claim this particular isomorphism, then our original ring R, what is our original ring R? Z mod 6Z. Okay, this is R prime. This is adjoining. This is R prime is nothing but R of 3 bar inverse. Okay, R of 3 bar inverse. Okay, it's an extension ring. So in this, if you see, once I prove that this R prime is isomorphic to F2, this F2 has 2 elements, then the original ring Z mod 6 has 6 elements. Therefore, it is not there is no injection from 2 element set to I mean 6 element set to 2 element set. Okay, so this, okay, first we prove this isomorphism, why it is this is true. R prime is isomorphic to F2. First note that our R prime is nothing but Z mod 6Z of X quotienting by ideal. Okay, some ideal. You see, already we have quotiented by 6Z, okay, with the ZX over ZX, and then we are quotienting once more by the ideal, which is same. I mean, this is same as saying that quotienting put together. Okay, there are two relations: 6x equal to 0 and 3x minus 1 is equal to 0. So therefore, this this particular quotient ring R prime is isomorphic to ZX modulo the ideal generated by 6 comma 3x minus 1. This we have seen already. R modulo I is isomorphic to R bar modulo I bar. Okay, because I bar to R bar modulo I bar. So you see this ideal containing 6. Therefore, by the correspondence theorem, the third isomorphism theorem, this will follow. This isomorphism will follow. Okay, in this what are all relations we have? We analyze the two relations. We are quotienting by ideal generated by 6 and 3x minus 1. So 6 equal to 0 first of all, and 3x minus 1 is also 0. 6 is 0 means 6x, which is nothing but 0 times x equal to 0. Therefore, 6x minus 2 is 0. Why 6x minus 2 is 0? Because 3x minus 1 is 0. Therefore, 2 times 3x minus 1 is also 0. That is nothing but 6x minus 2. Therefore, since 6x is 0 and 6x minus 2 is 0, therefore 2 equal to 0. If 2 is 0, then 2 times x is 0. Therefore, x minus 1 is 0 just because you see 2x is 0, 3x minus 1 is 0, therefore x minus 1 is 0. Therefore, hence the ideal generated by 6 and 3x minus 1 contains 2 and x minus 1. So therefore, the ideal generated by 2 and x minus 1 is contained in 6 comma 3x minus 1. On the other hand, this 6 and 3x minus 1 is already inside 2 comma x minus 1. What does this mean? Why it is? So because 6 is inside this particularly. Why? Because 3 times 2 is 2 is already inside this ideal. Therefore, any integer times that thing will be inside. Therefore, 6 is inside. 3x minus 1 is inside because x minus 1 is inside. Therefore, 3x times x minus 1 plus 2. The 2 is also inside since it is ideal. Okay. So therefore, these two ideals are one and the same. Means ideal generated by 2 and x minus 1 is same as 6 ideal generated by 6 and 3x minus 1. So therefore, the ring extension ring R prime is isomorphic to ZX modulo the ideal generated by 2 and x minus 1. First we divided by x minus 1. X minus 1, when we quotienting it by x minus 1, it means x equal to 1 we are putting. Okay, that is nothing but z. So then we are putting modulo 2. That is nothing but F2. Okay, so this quotient ring is isomorphic to F2. So F2 means the Z modulo Z6Z. This is not inside F2, just because here it is cardinality 6 and it is cardinality 2. Okay, so when we have the relation, some element we want to attach, and that element satisfies a relation non-monic kind of polynomial equation, then we are not getting the extension of the base ring. Okay, it is not even inside, it is nothing to do with it. Okay, so but the point is, when we take monic relation, this ring is sitting inside. Okay, so this is the catch. Here we looked at kind of very particular. A times b is 0, where okay, this kind of elements are called, already you know possibly, an element A of the ring is called a zero divisor if there exists a non-zero element B such that A times B is 0. Okay, for example, 3 is a zero divisor in Z mod 6Z, because 2 times 3 is 6, which is 0 here. Okay. So if zero divisor is there, then we are unable to, when we attach a inverse of a zero divisor to the given ring, then that is not an extension. Okay, that's what we are finding it in this particular page. Okay, so we want to kind of avoid such a rings. What are the other what are the rings we need to avoid such that our extension is always kind of inside the, I mean, the extension always contains the subring of the given ring. Okay, so this section is talking about integral domains and fraction fields. The difference between rings and fields is that non-zero elements of a ring R do not necessarily have inverses. In this section, we discuss the problem of embedding R as a subring of a field. Okay, here you see, here zero divisors are there. Z mod 6Z has a zero divisor. This we are not able to push it inside a field. At least in this example, it is not contained inside field. Okay, the extension, natural extension ring is not inside. It's a field, but the point is it is not containing the given ring. So here we want to solve. Okay, here we want to solve the given ring when the given ring will be a subring of a field. Okay, embedding means we want to find a injective homomorphism from R to a field. That's all for some field K. Okay, so when it is possible, as we have seen in the previous discussion, that we cannot adjoin the inverse of a zero divisor without killing some elements. Hence, the ring R with zero divisors cannot be embedded into a field. That is the counterexample we have. Okay, so we want to kind of avoid the zero divisors. So that is the definition. An integral domain R is a non-zero ring. First of all, integral domain means it's a non-zero ring. It means 0 is not equal to 1. Okay, having no zero divisors. In other words, if AB is 0 for some A comma B inside an integral domain R, then either A is 0 or B is 0. If such a so any, for example, any subring of a field is an integral domain. Okay. Okay. So we want to embed every integral domain inside a field. Okay. There is a kind of natural field is coming. First integral domain is Z. Okay. The very known integral domain is Z. Z is sitting inside Q very naturally. Okay, that is the one model we are going to follow. Okay, so an integral domain R, what is the extra kind of consequence of no zero divisors is the cancellation law in the multiplication. An integral domain R admits the cancellation law. If A times B equal to A times C for a non-zero element A in R, then we can cancel that A. Okay, multiplicative A. Okay, so B equal to C we can get. Why it is? Since AB equal to AC, this implies A times, because of distributive law, A times B minus C equal to 0, where A belongs to R and B minus C belongs to R. Okay, A times B minus C is 0. R is an integral domain, therefore A is non-zero element, therefore B minus C has to be 0 by the definition, okay, of integral domain. So therefore it means B equal to C. The cancellation law holds. This is the advantage. If R is an integral domain, then R of X, the polynomial ring, is also integral domain. Okay, R is an integral domain, therefore polynomial ring Rx is also integral domain. Okay, therefore we can keep on adding adjoining, variable, one variable, two variable, three variable. If R is an integral domain, therefore R of x1, x2, xn is also integral domain, right? Okay, so R is integral domain. Then R of x is y, it is an integral domain. Just we take two element in R of x, product, we take a product and we equate it to 0. Here two elements are polynomials. Okay, polynomials f of x times f of x and g of x, which is equal to 0 means we are not equating to 0. 0 means it's a 0 polynomial. We are assuming it's a 0 element in R of x. Okay, suppose if it is 0 element in R of x, what does this mean? It means after taking the product, each coefficient is 0. That is the assumption we are making. Okay, if f of x times g of x is a 0 polynomial, then suppose f of x is kind of is a polynomial. Therefore, you write it like a0 plus a1x plus etc. am x power m. And g of x is a polynomial b0 plus b1 etc. bn x power n. Okay, then f of x times g of x, which is nothing but summation l equal to 0 to m plus n cl x power l. Okay, where cl is in terms of ai and bj's. Okay, where I plus j equal to l, precisely I plus j equal to l, sum over all I plus j equal to l, ai bj. That is what cl is. Okay, by assumption all cl's are 0. In particular, cm plus n is 0. Cm plus n is 0 means the leading coefficient. Leading coefficient is 0. But the point is, the leading coefficient Cm plus n is nothing but am times bn only. That is 0 means, since R is an integral domain, and by the definition of leading coefficient of the polynomial f of x and g of x, am is non-zero, bn is non-zero. Therefore, the product cannot be 0 because R is an integral domain, which is a contradiction. Therefore, okay, so what we have proved, it must be an integral domain. Two non-zero polynomial cannot be equal to 0 polynomial. A product cannot be equal to 0 polynomial. So it means it is in R of x is an integral domain. So therefore, in corollary is that R is an integral domain, then R of x1, x2, xn is an integral domain. Okay, by inductively. Another proposition is an integral domain with finitely many elements is a field. This is okay. Integral domain and the field. What is main difference is, okay. So every non-zero element in the integral domain should have an inverse, multiplicative inverse. That's all we have to prove. Okay, since R is finite, we write it like a1, a2, an. These are the elements of R. We take x is an element of non-zero element of R, and we multiply by x every element of R. That is x dot R is same as x dot a1, x dot a2, etc., x dot an. Since R is a ring, it's a closure property. Therefore, this x dot R is same as R itself. Okay, R itself, because you can check that it cannot be because R is an integral domain. This cancellation hold. Therefore, each element has to be x dot ai equal to x dot j. Then x cancels. Therefore, ai equal to aj. It means all elements are different and its cardinality is n. Therefore, similar to, and it is inside R. Inside R, because it's closure property of ring R, it's inside R. Therefore, x dot R equal to R. Okay, since one belongs to R, one belongs to x dot R also. It means one can be written as x dot ei. That it means x as a multiplicative inverse. Okay, so this means any finite integral domain is a field. Okay, it's needed later. Okay, so in this section, what is the main goal is? Main goal is we just saw that okay, there is if you take an arbitrary ring and there may two elements may be there. such that whose product is 0. Okay, then if such a element we cannot adjoin the inverse of that such an element. Okay, so that gives a problem. Why? Because if we take that extension, then that extension doesn't contain, first of all, it may not contain the basic ring also, base ring also, and we cannot put it inside in general field. We want to classify all the subrings, all the rings which can be embedded inside field as a subring. Okay, so for that we have taken a smaller class of rings which is called integral domains. Okay, integral domain, we want to push this integral domain inside field as a subring. Push this means injective homomorphism, because image of a homomorphism of a ring is going to be a ring. Okay, which is images, if it is injective, then the R is isomorphic to the image of the homomorphism. This image of R is contained inside that field. Therefore, we say that R is sitting inside the field. Okay, so we want to create a field. Given R integral domain, we want to create a field such that there exists an injective ring homomorphism from R to F. Okay, we could have easily constructed, we could construct the field by adjoining the inverses wherever inverse was not there. Okay, so whatever multiplicative inverse, some elements may have inverse, multiplicative inverse in R, you leave out that. Whatever elements it doesn't have inverse, you start adjoining. Okay, to R, first alpha 1 alpha 2 alpha n, or does it have the inverse? Then first you consider R of alpha 1 inverse, then you assume this ring, then you consider R of alpha 1 inverse, alpha 2 inverse, etc. You keep on adjoining all the inverses, you can hope to get a field. Okay, that is one way to do that. There is a simpler way to construct a field with fractions. Our model is the construction of rational number Q. Okay, as a fraction of fractions of integers. So any rational number will look like a by b. A is an integer, b is integer, where b is non-zero integer. So same thing we want to follow. Okay, R is an integral domain. A fraction is of the form, a fraction of R is of the form a by b, where a and b are belongs to the ring R and b is non-zero. Okay, so two fractions, you see in in the rational number, 1 by 2 is same as 2 by 4. Okay, so we really say that it is equivalent. Similarly, we want to say that two fractions formed from the ring elements, integral domain elements, a1. So we take a1 by b1, a2 by b2. We say that these two fractions are equivalent if and only if the cross multiplication is equal. This cross multiplication, a1 times b2, this is an element of ring R. a2 times b1, it's an element of ring R. These two should be same element, representing the same element. Then we say that these two fractions are equivalent. This relation is an equivalence relation. It is just trivial to check. Okay, equivalence relation means first of all, A is related to A itself, then A is related to B, then B is related to A, then transitivity, A is related to B, B is related to C, then A is related to C. Okay, so this equivalence, this is an equivalence relation. The field of fractions, field of fractions F is of R is nothing but the set of all equivalence classes of this particular equivalence relation. You collect all those equivalence classes. Okay, we call this set as F. We want to define addition and multiplication so that this becomes a field. Okay, this is what is the addition? A by B is an equivalence class now. Okay, yeah, I am just writing it like maybe we should have written a square bracket, but I am dropping the square bracket of A by B. A by B is a kind of representation. Okay, A by B plus C by D. Two fractions I have taken, equivalence class I have taken, I am adding. What is the addition means? I am looking at the equivalence class of AD plus BC by BD. Okay, you see when A by B is defined means B is non-zero, D is non-zero. Okay, A is B is non-zero, D is non-zero. Therefore, B times D is non-zero. Why? Because it is an integral domain. Okay, therefore the fraction is defined clearly. AD plus BC by BD. It's a fraction. Okay, if the below whatever we are putting it should be non-zero. Okay, this is the way we are defining addition. Multiplication is AB times CD is same as AC by BD. Again, BD is non-zero. Therefore, this equivalence class we are taking as multiplication. Okay. So here A by B is an equivalence class, not an element. We are just using the same. Okay. Okay, so I have not really checked that it is indeed a field. Okay, so what is the zero element? Zero element will look like 0 by a non-zero element A. Okay, that is a zero element because this represents an equivalence class. And 1 by 1. That is the unit element in this particular ring. F. Okay, R is contained in F. Why R is contained in F? Just because you see we can identify R element of R by A by 1. Why? Because you see this identification makes sense. So because A by 1 is equivalent to B by 1 if and only if A equal to B. Okay, so therefore this fraction makes sense. So therefore a map from from R to F, how will we give? A to A by 1, the fraction. This is injective homomorphism. Okay, only thing is that what I have not checked is with respect to this, it's a group. With respect to this also, it's a group, it's a commutative thing. Okay, it's a field indeed. Okay, I have not checked it. Okay, I just overboarded. Okay, only one example. K is a field, R is like K of X polynomial ring. If you take, since K is a field, it's an integral domain. Therefore, R is an integral domain. Means K of X is an integral domain. So K of X is an integral domain. Now we are looking at the fraction field of K of X. What is that fraction field will look like? It's a fractions from the ring R. Any element of the ring R is like a polynomial, two polynomials. Okay, when we quotienting that below 1 should not be 0. Okay, it should not be 0. It should not be zero element. Okay, zero element here. Zero element means it's not a zero polynomial. So it is like a rational function f by g, where f of x is a polynomial, g of x is a polynomial, where g of x is non-zero polynomial. Okay, so this equivalence classes of fractions of this f by g. This is a fraction field. This fraction field is called. This fraction field is called the rational functions, field of fractional functions with coefficient in K, the field K. Okay, I am just overboarded. Okay, I stop here. So far we have seen only the G. Okay, we have extended the ring by ring extension by adjoining some new element. When we adjoin inverses of some zero divisor, it was creating a problem. Therefore, we just class of rings we chosen. That class is called integral domains. In this integral domain, there is no zero divisor. Therefore, we can adjoin inverses. It means we can really go from the ring R integral domain to a field. That is the process we are defining. Okay. So the given ring R, if it is an integral domain, we can push this ring R into a field. So the way Z is sitting inside Q. Okay, that's the lecture of this. I stop here.